Hello everyone, welcome to Study EETech, the home for electrical engineering students. How to draw transformer phasor diagram. The transformer phasor diagram seems to be one of the most difficult topics in electrical engineering. What makes the transformer phasor diagram so difficult? That is the way of our understanding, the way we learn it, the approach. That approach makes the whole thing very difficult. Let us admit one thing, the transformer phasor diagram looks very difficult, but I will give you here the step-by-step approach, the logical approach, so that you can build your concept to draw the transformer phasor diagram. And I recommend you to watch this video from starting to the end so that you can get the whole concept in a very simple way and remember this thing forever. That means you get the concepts very clearly. Okay, so let us go to the next slide and let me change it to the pen. Okay, so this is the ideal transformer. Okay, so what is a transformer? Ideal transformer meaning there is no winding resistance, no hysteresis eddy current loss, and all the flux are confined within the magnetic core. That makes the ideal transformer. That in reality that doesn't happen. Well, what is a phasor? Phasor is a rotating vector. We know scalar and vector, and whenever you rotate the vector, that rotating vector creates the sinusoid. So basically sinusoid and the rotating vector is same thing, and for the sake of simplicity we take the vector here, and the snapshot of the vector at any instant of time, that becomes the phasor. And all many phasors in a diagram called the phasor diagram. So how many phasors are here? V1 is a sinusoid, E1, phi, E2, all they are the sinusoids. We call them phasors. So first step is find out which is common in between these two circuits, the primary and the secondary. What is common? The flux is common. So we take the flux phi m as a reference phasor. Now who is developing this flux? That is the current Im. Im is drawn from the supply. That Im is setting up this flux. We can say Im and phi will be in same phase, because whenever there is Im, there will be phi. Whenever there is no Im, there will not be any phi. That's why we say the Im and Im is in same phase. Now E1 and E2 will be 90-degree lagging. Why it will be so? Let me prove it. Quickly I will prove it. Let me take that color, it looks good. Let us say phi equal to phi m sine omega t. Okay, now develop E1 will be minus n1 d phi dt. Phi is this one. Okay, taking the derivative of it, it will come to be E1 max sine omega t minus pi by 2. If you can't do this derivation, it's very simple. Take the derivative of it, minus minus will get cancelled out, pi by 2 minus omega t, this will come. Okay, this is simple mathematics. So what is happening here? E2 is 90-degree lagging minus pi by 2. So this will be 90-degree lagging to phi. Similarly, E2 will also be same way, because due to this phi E1 is developed, same flux is cutting E2, so the phi 2 will be developed, will be in same phase with E2. Now E1 and E2 length will be decided by the number of turns N1 and N2. Now look, V1 and E1 will be in opposite phase, because the transformer, the Lenge's law has to be satisfied. E1 is developed due to phi is developed due to Im is developed, Im is flowing due to V1. So E1 will oppose V1. So V1 is in 180-degree phase separation with E1. Okay, so this is a phasor diagram. So you got the steps: first phi m, then Im, then E1, E2, then V1. Now we will connect some. Now we will deviate to the practical version of the ideal transformer. Now in earlier case, from the primary the current was drawn equal to Im. Now there will be extra current flowing. Along with Im there will be extra current. Look, the transformer phasor diagram remains same, only we have taken IW, right? So this Im in previous case here it will also be present magnetizing component. This IW is called core loss component. This is reactive component, that is active component, and this is sometimes called what? Full component, and sometimes this is called what? Less component. Okay, because this core loss, what is core loss? This, in the transformer there is iron loss plus, sorry, not iron loss plus, core loss or iron loss, same thing. There are two things, one is hysteresis loss and there is the eddy current loss, and they appear as heat, right? So they appear as heat, that's why this is an active component, and that will be in phase with, active component is always in phase with the voltage. Okay, it's like resistance. So V1 and IW will be in same phase. This IW plus IM will make the current IO, and that is a no load current. So right now the transformer is drawing only the no load current. Okay, now what we will do, we will connect some load. Let us do that. Now we have connected some load. Okay, some current will be flowing here, I2 current will be flowing. Now look, everything remains same with respect to the previous one. Now we have just added this one, this I2. We have assumed some current is flowing here, current is flowing here, I2. So this is the I2, lagging current. Okay, so this current will have reflection on the primary side. Understand this point clearly. Whenever I2 is flowing, I2 has to oppose its region. What is the region of I2? I2 is developed due to E2. E2 is developed due to phi. So I2 has to oppose the phi. So how I2 will oppose phi? The I2 will oppose phi in this way. It will develop its own flux. It will develop its own flux called the secondary flux, and the main flux is downwards, and it will generate, or it will develop in its own flux in this direction so that it can oppose it. So the Lenz's law is satisfied. Now we can say there is a decrement of phi. So if there is a decrement of phi, there will be a decrement of E1. If there is a decrement of E1, the difference is increasing, so the I will increase, I1. So there will be increment in the primary current. So if there is an increment in the primary current, again phi will increase, remaining phi will constant. I have explained this thing in this way to tell you that the phi will remain constant. So whenever the current is flowing from the secondary side, the load is drawing current from the secondary side, that current will be compensated, to make this flux constant, will be compensated by drawing extra current from the supply. What is the extra current? Let us say that is a I2 dash. So basically I2 will be reflected as I2 dash in the primary side. So if this is your I2, I2 dash will be in the primary side. Now the primary current has three parts. One is IM plus IW as it is, plus I2 dash and I2 dash, and this is called the no load current I0. Okay, so this is a, and this is a I1. Okay, so this is a phasor diagram for the case whenever the load is connected. Now I will tell you the transformer equivalent circuit. Basically whatever I told you, we can present all these things in this diagram called the equivalent circuit. This is the transformer. Now look, this is the ideal transformer, this is a transformer part, this is N1, this is N2. Now look, this primary current, this is a I1. Okay, this I1 has three components. One is IO and one is I2 dash. IO has two parts, IW and IM, and this is RC and this is XM. What is it? They are the core loss component and the magnetizing reactance. Okay, now look, I1 equal to IO plus I2 dash and IO equal to IW plus IM. Clear? And these are the winding resistance. This primary side will have some resistance, this is the resistance. Secondary winding will have some resistance, that is a resistance. And this is not entire flux is confined within this magnetic core, so there is some leakage flux which is linking only coil 1, that is represented as a primary leakage reactance. Same thing happens for the secondary side, that's why there is a secondary leakage reactance. So that is the equivalent circuit of the transformer. Now we will connect the load. We consider the load to be lagging first. Okay, so what will it be? Now look, everything remains same. I'm telling you, phi, first you draw this phi, first you draw this phi, right? Then you draw this IO. IO is basically IM plus this IW, that is not shown here, that is IO. Now let's say some current is flowing I2, some current is flowing, let's say I2, right? So I2 has some reflection on the primary side like previous. So this is I2 dash. Now I2 dash and IO makes I1. Okay, I1. Now look, this is E1 and this is E2. Okay, this is E1 and E2. They will be 90-degree phase quadrature to phi. So now we can say if this is your I2, right? So this will be V2 because we have considered the load to be lagging load. So current is lagging by phi 2. Okay, now this V2, now look here, some KVL equations. We can say this V2 equal to E2 minus this drop equal to V2. So we can say V2 plus this equal to E2. V2 plus I2 R2 plus I2 X2 equal to E2. And similarly here E1 plus I1 R1 plus I1 X1 equal to V1. Okay, we will put all these things in the phasor. Now we have already V2, so this is up to this is V2. Okay, this V2 plus I2R2, and I2R2 and I will be in same phase. That's why I2R2 is parallel to I. Okay, this is your I2R2. Now I2R2 and I2X2 will be at 90-degree because this is for the inductance, voltage and the current will be in 90-degree. So I2X2. Okay, and this 9-2x2 will end up at E2, so that we get E2 equal to summation of these voltages. Same concept will be applied here. Now for the primary side we take the minus E1 because this is in this side, so we have to, and this is the voltage in the primary voltages are in this side, so I take the equal and opposite of E1 as a minus E1. Okay, so E1, this is E1, assume E1 plus IR. Now current flowing is I know this one is I. So parallel to this will be IR, I1 R1, right? Parallel to this. 90-degree to this will be IX, 90-degree to this IX, and that point to this point will be the V1 to the voltage. So that way the transformer phasor diagram is drawn. Now we will do the same thing for the other loads. Now let us take, we have done this one, right? We have done this one. Now we can compare with that. Now I will take the what we will take. Let us take the unity power factor load. Let us say V2. V2 was here. Look, V2 was here, and this was phi 2. Now I will make phi 2 0. Unity power factor means V2 and I2 will be in same phase. V2 I2 is in same phase. Look, V2 I2 is in same phase, right? Now this is the IR drop in same phase. Then IX drop 90-degree. You get E2, right? Same concept will be applied here. This I2 will be reflected as I2 dash here. It is not shown. Oh, basically the vector is shown here, the triangle method. Anyway, the thing is same. You can get this one, I1. Okay. Now this minus E1 plus IR drop plus IX drop will make V1. Similarly, here the lagging, the current is in this side. V2, take the V2 as common. This side lagging, same leading, unity power factor. Here the current is in this direction, meaning the current is leading the capacitive load. Now the remaining part is same. You have to take the IR parallel to I, so this will be this, and 90-degree to it will be IX, and that will be E2. And similarly, this current will be reflected somewhere in this side, which is nothing but this one. That will be I1. Okay, I1. So E1 parallel to this line will be IR drop, this will be IX drop, and this will be the V drop. So this is the logic. You just apply this logic to draw the phasor diagram step by step. What I told you, you will remember forever. Okay, so that is the end of this discussion on the transformer phasor diagram. If you have any questions, you can put it in the comment box. If you like the video, share among your friends, subscribe the channel for more updates, click on the bell icon. Okay, so see you in some other lectures. Okay, thank you.